All, I'd like to start a bit early by apologizing. I've slept way too little, and I'm quite sure that I'm actually I have the flu at the moment, so my energy levels aren't nowhere near the normal stuff. So if I seem a bit lethargic, or if I go there and sit down during the lecture, please do try to understand.
Do we need to bring you coffee or something?
I have coffee and I have water, and I've already basically doped myself up with coffee. If I take any more, then I need to go to the toilet, and you don't want to start listening to me having a lecture while sitting on the toilet. And I apologize for that as well. But I think it's about right. So, welcome one and all to my lecture, Critical Overload. If someone doesn't know what they came in for, we'll be talking about different methods of power generation, both in antiquity, modern times, as well as certain parts of sci-fi and other kinds of fiction. Hello all, my name is Arttu Leinonen. Now I've actually introduced myself. Always good to remember. So, first things first, what is this lecture about anyway? Well, as I already started, different kinds of existing or plausible methods of generating power, electrical or mechanical, doesn't matter. And here we use the term plausible. So, as I think we all know, in different kinds of fiction, there are some generators that are simply hand-waved or something like that. So we'll stick to the ones that actually have at least some kind of theory behind them. What we go through them is what happens if some bloody idiot, I meant the captain, decides that for some reason we need more power to whatever thingamajig that the captain is worried about, and even though the reactor is already going at the maximum safe output levels. So what happens if we basically overload the generator, try to run it at higher speeds, higher energy densities or whatnot than it's actually been designed for? And basically, when that, for some reason or another, fails catastrophically, what is the worst imaginable thing that could theoretically be caused by the critical failure? So if worst comes to happen and all the containment methods that we have just fail or aren't actually there, what happens? All of these power generation methods can, of course, have normal failure methods, like 99 times out of 100, they will do something quite less catastrophic than what I'll go through here. But this is that once in a million chance. Luckily, everybody who's read Terry Pratchett knows that never happens. So, this is one of your chances to actually leave the lecture hall. If you don't, you will be hearing about how different power plants could go boom, or weird ways that we could generate power in the future, since I'll be going through quite a lot of science fiction examples. Or the weird ways that those science fiction reactors could go boom. Spoiler alert, way bigger booms than the ones that we have currently. And then we get to the part of disclaimers. First off, I am not an electrical/power engineer, or power production engineer. So I don't actually study this scientifically. I do not work with these things in my day-to-day life. So, you know, I'm not an actual expert on this matter. I am an engineer, though, and power production, and especially the ways that power production failures have been portrayed in different kinds of fiction. I'm looking at you, United Films made in the Hollywood, is a pet peeve of mine. So I've been reading quite a lot about it, to be honest. This is also not going to be an exhaustive listing of the different kinds of generators that we can have in science fiction, because, well, the list is endless. And I mean endless. So cherry picking is always necessary. And as I mentioned earlier shortly, some power generation methods are simply hand-waved. No one even mentions how this works. They just, it's the reactor, it's the drive core, and nowhere is it said how that drive core actually produces energy. Also, I am not touching the utterly ridiculous generators that there are. So, there is going to be no discussion to be had publicly, or at least I'm not going to be talking about the pros and cons of power generation by using, say, kittens as a power source. I know one type of fiction that actually has a kitten generator. It's a mess, to be honest, a bloody mess, to be exact. Also, I am, just to be clear that no one has any weird expectations, I am not going to touch the improbability generator in The Hitchhiker's Guide to the Galaxy, because that thing is simply broken. It breaks any game system that you try to use it in, because it's by definition broken. Also, I am not advocating you to abuse your power sources. If you have a chief of engineering or head of engineering or whatnot, do listen to their advice. Any and all abusive relationships with your power sources need to be consensual and based on mutual respect for each other. Just, you know, putting this out here. So, let's move on to the basics of power generation. So, I expect that not all of you are actually engineers, and not all of you are actually engineers that work in power production or industrial scale processes. So we'll go through shortly what we actually mean when we say power production or power generation. First off, what do we mean by power? What is power? Well, not political power anyway, but in this lecture, in essence, power is any force that can be directed by an operator through various mechanisms to manipulate the environment, if you want to get technical. In, you know, layman's terms, something that makes things happen when you push a button, or flip a switch, or, you know, turn the joystick, or whatever. You do something small, and then this pipe blasts a huge ray at the nearest planet or something. I don't know. The thing that allows you to make your things go harder, better, faster, and or stronger if you increase the input to that thingamabob. So you have your engines, you go at, say, 10 kilometers per hour, you increase the power input to the engine by 50%, and suddenly you go 15 kilometers per hour, or whatnot. Your shields can take more hits, or whatever. And usually this is in exchange of those things, shields, engines, whatnot, throwing up sparks of electricity, or breaking apart small pieces of them, or just, you know, starting to vibrate in a slightly worrying way. And power can either be mechanical or electrical. I've differentiated them slightly, but mostly in any sufficiently advanced society or setting, these two things are basically interconvertible. So if you have mechanical energy, you just stick a electricity generator on it and you get electricity. If you have electricity, you just use an electric motor and you get mechanical energy. So it's all the same which type we generate. In certain very low level settings, this might actually be a problem, but in those settings, it's usually highly unlikely that you'll be generating electric energy anyway, so I just, I'm not touching this. Then, what do we mean by a generator? And this is where this lecture will deviate slightly from the accepted scientific terminology. Because layman's terms, they are confusing. People who do not know how to speak properly use the wrong terms, and so when someone hears generator, they usually don't start to think of the thing that science and engineering types think of when they hear generator. Because scientifically, generator is a machine that converts mechanical energy into electricity, and nothing else, nothing more. But in this lecture, a generator is a self-contained machine that creates power without direct mechanical involvement by the operator directing the power output. So basically, there aren't going to be any hand-cranked devices. There aren't going to be any, you need to pedal this bicycle to actually generate energy or that kind of stuff. It's basically something that functions over there, and then the energy comes over here, and then in here you press a button and the power continues forward. So this is basically what we are talking about here. So we combine the method of generating mechanical energy and possibly electricity, and yeah, as I said, we move, for example, the self-pedaled bicycle generators. And then, what do we mean by plausible? Something that we have a sufficient semi-coherent theoretical framework to extrapolate from. So basically, if you have a wave motion generator or something like that, that we don't have any inkling even as to what physical forces or what physical phenomena it is using to actually generate the power, we won't be handling that here. And the theories, although, they don't necessarily need to be accepted, correct, or even complete, as long as we have someone has said that, well, this generates power by vacuum or something. It's enough. We can theorize how to generate power from a pure vacuum, actually. Just as long as we have something to go on, other than kittens, because, come on, kittens. And we will stay grounded in the material world, and thus all generators based on captured divine beings, demonic entities, or any other extraplanar self-aware or even semi-self-aware beings are not going to be considered. Because, well, we don't have a scientific theory on how angels actually work, so go figure. And of course, you need to remember that if you use one of these in some of the mechanical or the basic generation methods that we are having, they probably will increase the power output by quite a lot, increase the stresses on the machinery by quite a lot, and you get the additional problem of how about when those angels or demons or extraplanar xenomorphs actually escape your containment. But that is something that you need to just, keep in mind. Then we need to talk about the installation location. So as I mentioned, this is mostly about generators and reactors. Most of these could be used with some miniaturization in movable vehicles. Although, for some of these methods, it's going to be slightly more difficult than for others. And yeah, unfortunately, some of these reactors are so unwieldy that they need to be installed around a certain stellar mass object. So that does create some. But then again, if you have a large enough spaceship, you can use even some of the more unwieldy versions. Then a short discussion about the methodology, how we do things here. I created this approximate logarithmic scale that is used for the impact. So, you know, on a scale from 1 to 10, how bad is it if this type of reactor goes boom? And as I mentioned, the scale is logarithmic. So the format is what is the damage that has been caused, and then what is needed to actually restart power generation. So what we need to do to, you know, fix the reactor. Levels 1 and 2, these are easy. These are the safe ones. Basically, no fatalities, possibly some minor injuries or major injuries, but no fatal injuries. And basically, you just need to repair the reactor. Then from 3 to 5, we get the fatalities scale. So there's from limited to severe fatalities, and then either we need some reconstruction of the reactor, so basically swap out half the parts that have been melted in the reactor, or then the whole building that the reactor is housed in is basically unsafe, and we need to tear it down and rebuild it if we want to. Or then there's the, on 5 we start to get actual damage to the local countryside. So in addition to the reactor building being broken, if there's any buildings in the nearby location, say less than a kilometer, they will have their windows blown in or some slight structural damage or contamination from something. Then from 6 to 7, I'm sorry, we start to get you know, major fatalities. So at 6, the reactor site where the reactor is located is probably going to be a glowing crater. So you probably need to move the actual reactor site at least a few kilometers in one direction. And at 7, we start to get fatalities in the millions. A local nation is probably going to be quite decimated. There might even be some damage to the, you know, subcontinent. So, for example, Scandinavia might be a, well, let's just say less than pleasant area to be in. Then we get to 8. This is going to be quite bad for the local planetary population. So this is going to be a worldwide problem. Everybody's going to be affected. And it's possible that some of these might actually cause some damage to the local planet. So we might destabilize a few continents, or say America might turn into this hellish landscape of basically lava. Then at 9, we get a stellar extinction event. So basically any life in this or the local star system is going to go extinct. Or if there's going to be anything left, it's going to be extremely hardy cockroaches. And we might actually need to reconstruct the local planet that the reactor was located in. So the nearest planet, or if the reactor was situated on a planet, it might actually be a, you know, asteroid field nowadays. Then we get to 10, which is a galactic extinction event. So at least a quarter of the local galaxy is going to be basically sterilized. So good luck to your interstellar civilization from that point on. And, you know, moving to a more habitable galaxy might be a, you know, you need to think about it. Oh yes, and if you thought that this scale is going to stop at 10, you are seriously wrong. Because then we get to 11, which is an intergalactic extinction event. So basically, you done and fucked up the whole universe. So basically, if you want to continue from that, then I would suggest you try to find a dimension or universe that is more habitable than the one that you just broke. And because going to 11 is stupid, then there's the last one, which is, well, that did it. This is basically the level where we get to the fact that you are going to fuck up this universe, and depending on the how the actual multiverse, so multiple dimensions of one universe, are built and how badly you actually fuck up, you might actually destroy the nearest neighbors. Or if things go extremely badly, you actually fuck up the whole multiverse. So, well, that was it. Let's move to the next reboot of this comic series or something. Also, as you might have understood from the previous slide, we're going to discuss power generation methods that have slightly different scales. So the power output scale is also quite variable. We start with horses for the pre-modern and some of the modern generators. So a horse is approximately the equivalent power of one yoked horse that does perform physical work at a steady rate that it can keep doing for the whole day, which is approximately 750 watts. And for the record, I do not care whether the horse is English or French. They are close enough. The difference is 12 watts or 12.5 watts, something like that. So I am not going to be differentiating imperial and metric horsepowers, just for the record. Then we use watts for modern generators, usually with different kinds of kilo, mega, giga, tera, and so on prefixes. I hope that you have your SI prefixes at least somewhat in hand. If you don't, well, they go up, let's just say. And then at the last end, we use the Kardashev scale for too far out there generators. It's a logarithmic scale from 1 to 3 or 0 to 5 if you use the extended scale. We actually do need to use the extended scale because 3 is not enough. Humanity is considered currently at about 0.62, and this is basically a logarithmic scale. So at 1, the civilization can harness the output of the local planet, the whole total energy output of the local planet. At 2, they can harness the output of one star system, the whole power output of a single normal stellar class object. At 3, they can harness the power output of a regular galaxy. And at 4, they can harness the power of a single universe. And then at 5, they can harness the power of multiple universes. So it goes up a bit. And I do need to remind you that all of these values, or most of these values actually, are provided by the Stetson-Harrison method, where actual numbers are available, or where actual numbers are not available. So for the modern generators, I actually did try to look up the actual values, but for the pre-modern and the science fiction generators, I needed to, just make an educated guess as to where around-ish we are on the scales. So don't actually take my word on it. Then we have an example generator. So this is how each of these generator types are going to be introduced. This is the base slide that I've used in all of them. So we have the name of the generator, the type of power generator, which is ideal in this case, because it's an example, and it requires the information age about to be available. So if you are in pre-information age settings, this probably is not going to be working. This generator, for example, generates power by converting clarifying examples through memes into popular action. So you can see how that works. Maximum safe output power is about 1 nyan cat per hour. About. It's approximate. The most catastrophic failure method that is possible for this is unsafe cuteness, which causes brain damage. And the impact is, you know, quite limited, so no fatalities. And now, any questions so far? This is basically if you have any questions about the methodology or the scales or anything at this point. And also, this is your last safe exit point before we start getting technical. So, you know, you've been warned. No questions. Great. I'll take a sip of water. So, then moving on to the main part of the lecture. Generators. So, here we go. Prepare yourselves. First up, we have the running wheel. So, well, generates rotational mechanical power and was available already in the ancient era. So you don't even need to have, you know, classical Romans or anything. It was available for the Babylonians and such. And, you know, a running wheel, the kinds that we nowadays use for mice and cats and whatnot, and some office workers I've heard. I don't know. So enclosed wheel where power is generated by people or horses or draft animals or cats or whatnot running around, or demons if your setting is that kind. Maximum safe output power, approximate, 1 to 8 horses, depending on how large of a wheel you have and what's powering it. The basic that I've seen is basically 1 horse being in a running wheel. What's the most catastrophic failure method? Well, runaway wheel. So the wheel breaks its axle and starts, you know, rolling around with a panicked number of people or rats or horses inside of it. Not a nice sight. But to be honest, we aren't that far on the scale. So limited fatalities and limited reconstruction. We need to get the wheel back. We need to replace the axle. And, well, if you're unlucky, the wheel runs over somebody and they die. No, not that much. Not that much. The same thing can also be said for cranks. So if the wheel is not, or if the axle is not horizontal, but it's vertical, and you have push or pull bars, and then you have people pushing or pulling them, that's basically the same type. Although the thing is that it doesn't actually have the problem of the wheel escaping, so it's actually safer than this one. But anyway, I used this because it can cause more fatalities. I always go for fatalities. Next up, we have the water wheel. So now we moved slightly forward, still in the ancient era, at least for the really primitive versions, and generates rotational mechanical energy. Turns the potential energy of flowing water into mechanical rotation through a paddle, and used mostly in established manufacturers. Now, this power generation method, of course, has this one slight problem. You actually need to install it in a river or a body of water. I'm not quite sure how you could actually install this in a moving vehicle. If somebody can figure out a way, like, a safe or, sensible way, well, I'm all for that. But I fail to see a method. So this is mostly just for because, we're going through the generators. This can be upgraded with a dam to control the flow of water and also the level of the water. So if you increase the height from which the water enters the water wheel, you actually increase the power output of the wheel by quite a lot. Most power you can get out by actually dropping the water on top of the water wheel so that the water actually turns the wheel for a whole half rotation. But this increases the safe operating power, but it also increases the possible impact, because now we have the added problem of, well, we have a body of water that is dammed. If the dam breaks, there's going to be water that is released, so depending on the size of the dam. Most likely it's not going to be that big, but, still worth remembering. So, maximum safe output power. Oh yes, one thing that I, of course, forgot to mention. We are going through these generators one by one. So especially once we get a bit farther away, when the theoretical background for these generators might not be that clear to the layman, if you have any questions about them, do ask them when we are talking about the generator. I don't want to go back to a generator that's already been considered or handled, but we have the time, so we can discuss at least a bit each of these generators at the time we are going through them. Just pointing this out. But anyway, maximum safe output power for a water wheel is 5 to 30 horses, approximately, depending on the how high the water is actually flowing, how fast the water is flowing, etc. Most likely limiting factor is the strength of your water wheel, actually. Because if you only have wood and you might not even have iron nails, you can't really make that durable water wheels. Well, most catastrophic failure mode, mechanical failure due to flood. So you basically have more water flowing into the water wheel than you designed the water wheel for, and suddenly it just can't take the pressure, or the water wheel gets blocked up or locked down, and then suddenly starts breaking against the water that is trying to flow around it now. Impact is quite limited. It can break if the flow exceeds structural limits, and even getting a single fatality out of this basically needs that the water wheel axle is connected to some, hammer or something, and just when the wheel breaks, somebody's, pushing their head under the hammer. In that case, I say that they just win a Darwin Award, and we don't count that. Then the third power generation method, we have the windmill. So again, rotational mechanical power, because that is so easy to produce. That's actually why generators actually usually just turn rotational energy into electricity. This, although, requires classical era. So I didn't manage to find any examples of windmills before approximately, the Greeks and the Romans and that kind of stuff. So because it needs a bit more effort in constructing, because you need to actually construct a tall building, and also you need to think about that. Oh yeah, there's air thing that is moving against my face. I could perhaps use it for something. Turns the movement of air into mechanical rotation through axles, etc., etc., etc. There's actually quite a bit more machinery involved in a windmill than in a water wheel, because you need to actually be able to rotate the windmill, because the wind is most likely not going to be blowing from the same exact direction every day of the year. Also, possible additional hazard to windmills is questing or errant knights that try to, joust them to death. So, do remember to look out for those. Maximum possible safe output power, 1 to 2 horses. Not much, honestly, not much. But then again, you can build these anywhere, not just near rivers, so that's a good point. Most catastrophic failure mode, mechanical failure, so basically the windmill breaks for some reason. An axle is broken or somebody throws a monkey wrench into them or an axle breaks or something. And here we actually, it's unless the actual windmill collapses on top of somebody, it's most likely not going to kill anybody. Like honestly, not going to happen. Then we move to slightly non-standard power generation methods. So a magical running wheel. So either generates magical or rotational mechanical power. And you usually require some sort of magical engineering technology or skill in your civilization. Even though you have mages, they probably are not able to, just start building machines that make use of that magic without the mages actually all the time doing something for it. So basically the same as a running wheel, but either you add magical crystals or whatnot that make the wheel run faster or produce more power or enhance the power output, or the running wheel is actually used to excite some kind of magical crystals or artifacts or objects that generate magical power. Good example, this is also easily weaponized. For example, in unscrupulous hands or paws, Skaven for anybody. They have the Doom wheel, which is basically a running wheel with attached magical thingamabobs that generates magical lightning as the wheel is turned and moves around the battlefield and basically just zaps people. Also heavily armored, and did I mention it's a wheel? It's a large wheel. It squashes people. Maximum safe output power for this, 20 plus something horses, depending on size. It just depends on how good your other engineering skills are, so how durable or what's the structural integrity of the running wheel that you are using. And of course the setting, if the setting is low magic, it might be that this doesn't really add that much. If you're in Warhammer, this actually, generates lightning, like at the drop of a hat or hood, whatever the Skaven use. Most catastrophic failure mode, runaway wheel, again, mostly. Then again, it might also explode. Again, depends on setting. Magic is one of those things that most settings don't actually have a comprehensive theory on magic. So I'm not quite able to actually, theorize based on those non-existent magic theories how the magical explosion might kill people. But yeah, usually these things can blow themselves up. So we basically up the fatalities a bit, and the running wheel is most likely going to be an X running wheel. Anyway, moving on. Now we get to the reciprocating piston steam engine, or the steam engine, as most people call it. So, Industrial Revolution, anybody? Now, this is fun. It actually creates linear mechanical energy, but also Industrial Revolution was the time when engineers finally figured out an easy way and efficient way of actually turning linear mechanical energy into rotational mechanical energy and the other way around. So basically, It's all the same, but by the essence, these actually generate linear mechanical energy, if that has anything. You know, the things in trains that go out and back, those things. So, creates linear mechanical power by creating and condensing water vapor in machine pressure vessels. So you basically have a piston, a long rod of metal with a flat end that is in a machined enclosure, that is the piston housing or the cylinder. And then you produce steam that is injected into the cylinder between the cylinder cap and the piston end, and then the increased pressure pushes the piston out. And then you can actually have two of these, so the cylinder is actually enclosed in both ends, although one end has the piston bar, the metal bar going through it, but that's actually, you know, enclosed or like tightened. There's a seal there, so you can actually, there's one pressure vessel on this side and the other on this one, and then when it's fully extended, you close the input into the first side and start inputting steam into the side with the piston or the cylinder other end and the piston cap, and then it retracts the piston. We can also use different kinds of methods to actually cause the steam to condense inside the cylinder. This is one other way of actually retracting the pistons, but we need some sort of method to actually do this cyclically. Otherwise, we have an engine that can push out the piston once, and then it doesn't work anymore. So to get the engine, you actually need to have these two phases so that you can apply the steam to extend the piston, and then again somehow retract the piston automatically. Safe output power of these depends on the model and size used. So the larger the engine, the more power it generates. Usually the limiting factor is, again, the mechanical engineering and the structural integrity of the steam engine. So at some point, the metals that you use are simply not strong enough to withstand the pressures you are trying to apply. And the range provided here is from the James Watt's original patent for the steam engine to a late 19th century railway locomotive engine. So the maximum safe output power is from 10 to 10,000 horses. So the range of the power output moves quite a lot. But this is again, the first value is when steam engine was first invented, and the last one is, or the upper end, is one of the last steam engines made before they became obsolete. So there's been quite a lot of technological advancements. So if your civilization has just started the Industrial Revolution, you're probably not going to be on the higher end. But then again, if you have a steampunk society that has been working or going under steam for, say, 50, 100, 500 years, you're probably going to be at the upper end and probably a bit further than that. Most catastrophic failure mode is boiler rupture for this one. So steam engines, they need to generate the steam somehow. That is usually done in a boiler, which is basically a metal vessel that has water at the bottom, and then there's a furnace underneath the boiler that heats up the water and thus generates steam. So basically, boiler rupture is when the boiler, the pressure vessel, the pressure inside increases too much that the boiler walls, the metal cannot actually stand the pressure, and it catastrophically fails. So basically, the boiler just blows up. Impact of catastrophic failure. Now we get get to, again, low fatalities. The engine is going to be scrap metal, basically. If the boiler blows catastrophically, the engine is going to be an X-engine. You need to build a new one. But fatalities basically depend on how early people start running and how fast they are at running. So if you give people enough head warning, they can move far enough away to actually get away from the explosive radius. But this, basically, if this happens suddenly, say in a train engine that is just arriving into a fully packed railway station somehow, it's going to cause quite a lot of fatalities, actually. It's basically good engine or locomotive engines that can pull, you know, let's say the Orient Express train, which is a long-haul train. The engines that can pull that kind of trains inside, they can have lethal radius to up to 100 meters. So basically, if there's no warning and for some reason people have packed near the locomotive, it can cause quite a lot of... It's probably going to get to the local newspaper at least. But again, depends.
Also cases on a ship.
Yeah.
Actually, the biggest maritime disaster in America is a steamboat engine exploding.
Yeah. That's if you have a steam ship or steam-powered ship, and you accidentally blow the boiler on one of those, the engine is going to be scrap, and so is the ship. So then the fatalities basically depend on the how many passengers and crew you have on the ship, and how far away are you from any safe place that they can swim to. So there were actually quite a lot of steamboats or riverboats that had boiler ruptures on the Mississippi. So, but that was actually why they started designing fail-safe valves. So, for some reason. But anyway, so this is steam power, and people love steam power. There's a whole genre for that. So let's move to the next engine, which is the ATHERIC engine. Actually, a resonant fluctuating ATHERIC engine, to be precise. So here we go quite deep into the steampunk genre. This generates electrical power and requires some sort of ATHERIC manipulation technology. And this is the point where I ask, how many in the audience actually know about the ether theory or the ether wind experiments? Some? Okay, good. For those of you who don't, ether, as it's when scientific people actually talk about ether, it was a theory in, I'd say, 19th century, when the Industrial Revolution had been going at full steam for quite a while, about how electromagnetic radiation works. Because at that point we had noticed that light is actually a wave, behaves as a wave, and as we know from water, wave is actually nothing but some carrier material moving in a wave-like fashion. So wave itself is not a matter, and at that point we had no idea that there was actually a photon to act as the particle or the material component of light. So scientists came up with ether, which is something that permeates the whole universe, that does not affect matter, but acts as a carrier medium for electromagnetic radiation, light and whatnot. There were quite many experiments trying to measure whether there was actually a wind in the ether, but these failed, and thus, in the end, the theory was decided that this was not how things actually are. Then we got the Foson. But what if the ether theory actually was true, that it was accepted and there was actually a medium that acted as the medium for electromagnetic radiation? In theory, if the medium was there and we had some way of actually manipulating it, it might be possible to actually generate a vessel of some sort, a chamber, that acts as a resonant cavity for ether waves. So we could create artificial waves in the ether, and then those waves would build up in the resonant cavity. And from that resonant cavity, because we are generating powerful waves in the ether, which, as I mentioned, acts as a carrier for waves of electromagnetic waves. If we have a resonant cavity where we have, a stable wave in the ether, that wave is actually electricity by definition. So we would actually create electricity from nothing, basically, forever. So this is the theory on how this could work. There are, of course, other methods of generating power from the ether that I can come up with in my mind, but those are actually just modifications of the methods, the windmills, water wheels, whatnot, that I've been talking about previously. So this is the only one that actually requires there to be an ether. Maximum safe output power, of course, we know steampunk. ATHERIC engines are usually the ones that power the Zeppelins and the god-awful sized machines that the mad scientists generate. So I'd safely say that we are in the more than 1,000 horses category. Most catastrophic failure mode, though, is an uncontained resonation feedback loop. So if we have a resonant chamber that is self-reinforcing, if for some reason our control over that resonant wave fails, for example, someone shoots a musket into the control panel or whatnot, if there is a positive feedback loop inside the resonant wave, which we actually need for this to actually generate more power than we put in, then we have this problem that the resonant wave is going to build up, grow, and grow, and grow, until at some point the chamber that we've used to contain it is going to say that, okay, enough is enough, I'm not gonna, and blows. And then we have an uncontained wave, a really strong wave in the ether that basically creates it might actually be quite close to an EMP pulse, although it's just, a wave that creates random sparks of electricity wherever it travels. Ball lightning, or lightning nova, if someone has played Diablo, might actually come quite close to what things look like at this point. So where do we get the impact for this? Now we get to the severe fatalities possibility. And, well, the engine is going to be scrap metal at this point anyway, probably a heap of molten slag, to be honest. And, well, the size of the impact, the actual size, depends, and of course the side effects of this depends on the structural strength of the resonant cavity, and of course where the catastrophe happens. If it happens in the mad scientist laboratory that is situated in their castle in the middle of Transylvania, fatalities aren't going to be that big of a problem. If it happens in the secret laboratory in the under the main railway station of the capital, there's going to be quite a lot of fatalities. So that's why we have a range here. And oh yes, about the structural strength of the cavity. If you build a thing that has a positive feedback loop, that you don't have a method of shutting down extremely fastly, and the method for shutdown must be something that cannot fail in any event. There is no possibility of it ever failing. Not because you can do it wherever you are, because it happens automatically via mechanisms that can't have failures themselves and so on. Always, 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 always build your reactors only as well as they need to be for the power output that you want. Don't build, if you build this kind of engine and the resonant cavity is just about strong enough to contain the wave at the level you want it to be to actually generate the amount of power you want, if you have a critical failure, the feedback loop is going to run for a few moments, and then the engine is going to blow and the effects are going to be limited. If you build it so that the resonant cavity can actually safely contain a wave that is 10 times as strong than the one that you are going to be using for power generation, you are just going to make the impact 10 times stronger than you need it to be without increasing your power output. So it's wasted research, which is always a bad thing, in my opinion. And well, you are only creating a larger bomb. Then again, of course, to be honest, that might be the intention, but well, I'll leave that to you. Any questions about this engine? Because this is the first one where the theory behind the engine is actually not quite clear. Okay. Yes?
Is there a possibility of some kind of radiation from this kind of engine?
Yes. As I said, electromagnetic waves, which means radiation. Only not alpha radiation, actually, because alpha radiation is actually atoms or nuclei. Oh, yes, true. Sorry, it's been a while since I worked with radiation science. But yeah, true. Gamma radiation you can still create, so that is an option. Any other questions? Yeah, of course. As someone mentioned, all their magical equivalents. So if the ether theory is correct, nothing is to say that there aren't any weird magical radiation types that actually are in the universe. So moving on, the internal combustion engine, again we return to the normal world. Rotational mechanical requires the industrial age to be produced. Generates mechanical power by oxidizing fuel inside piston assemblies, skipping the steam generation step of external combustion engines. So the steam engine that I was talking about earlier, that's the proper scientific term for that is actually external combustion engine. So the combustion happens outside the actual piston and cylinder assembly. If the combustion happens inside the cylinder, then it's by definition internal combustion engine. You could possibly use coal for that, but usually you are going to need some sort of gas or fuel because, trying to get an automated system to feed small lumps of coal into a cylinder 100 times a minute or whatnot is probably going to be quite difficult. To provide continuous power through operation cycle, usually multiple cylinders are used. So Steam engines can work with just one cylinder because they use the cylinder only to actually perform the work. But for internal combustion engines, they don't actually have the retraction phase. Steam engines can extend and retract the piston. External combustion, because they just combust the fuel inside the cylinder, they can't actually by themselves retract the piston. So you need, one piston that extends and at the same time pushes the other piston back in, and so on. And the safe output power depends on size and model that is used. Range is from the original patent by Benz from Germany, and the upper end is from a modern Wärtsilä marine diesel engine. The exact type is over there. From 0.5 kilowatts to 80 megawatts. So this is basically the point where we run out of horses. So we just don't want to start counting them anymore. Although I do need to point out that the original power is less than 1 horse. And the original steam engine produced enough power for 10 horses. So the first types of these that you are going to have in any setting or any civilization are probably going to be quite a lot worse than steam engines. And that is actually why steam engines were used quite long after internal combustion engines were available, because in ICEs have in certain ways they are better than steam engines or external combustion engines, but by pure power output, steam engines rule for quite a long time before you start getting modern heavy-duty diesel engines that finally are able to replace the old steam engines. That's, for example, why trains moved from coal-powered steam engines to diesel engines, because gasoline engines, that are the first ones usually invented, just can't compete as to power output. And the size is not a limiting factor. Most catastrophic failure mode is, well, basically destructive mechanical failure. So the engine somehow blows itself up. Usually this means that something has broken inside, and then what happens next is one of the pistons is going to go flying out of the engine in a random direction. They can actually fly quite far, and they leave a bloody big hole in the side of the vehicle. I've actually seen this happen I've seen the end results in a military truck. The engine actually blew while it was being used while I was in the army, and there was, I think, the hole in the side of the engine compartment was larger than my head, easily. So, as I said, low fatalities. Fatalities are possible. If somebody is standing in the direction where the piston is going to fly, they are going to be dead. Or, well, they are quite likely to be dead. Depends on how badly they get clipped. At the least, they are going to miss a limb or something.
So dead or wishing to be dead?
Yes, basically. But still, they aren't going to blow, so in that kind of, they aren't going to explode. Well, the fuel tank can actually explode, but that's a different thing. But the engine itself, it's not going to explode. And actually even the fuel tank, it's just most likely going to start burning, not really explode, but anyway. So there isn't really a lethal radius that much. If you happen to be in the wrong direction of the engine when the catastrophe happens, you are going to have a bad time. But other than that, it can hurt your ears, mostly. Then we get to the hydroelectric dam, which produces electrical energy. This usually requires industrial era, mostly because the size of the dams that are needed for this kind of site are going to need so advanced construction technology that even though during the industrial era they can build dams and they can create this kind of generators, but to actually produce any kind of usable amounts of electricity, it's easier to use steam engines. So these are most likely not going to be existent before. Oh well, actually, yeah, industrial era you can use, but the Industrial Revolution, the first stage is when industrialization starts. The electricity is going to be generated by steam engines. So, turns potential energy of flowing water into electricity, as well as acts as a water reservoir for the nearby area. So basically, steadies the floods of the river that they are building. For example, one of the reasons that the Three Gorges Dam was built is because the Chinese government didn't want the Yangtze to be flooding, so at least so catastrophically, every now and then. So nowadays, if it rains heavily, they just fill up the reservoir at the dam, and the river actually stays quite steady. And also, there's a dam upstream of the Nile, and they actually have this discussion because the dam is quite a lot south from Egypt, and Egypt needs the Nile to flood to actually replenish the soil in the farming areas. But the states that actually control the dam upstream, they don't care about the flooding. They actually don't want the flooding because flooding is bad for them. It's a flood. So they are continuously discussing that, okay, we want you to, release this much of extra water. Well, we don't want. Our citizens are going to suffer. So I've understood that it's an annual discussion that they are having currently, and it's quite heated, to my understanding.
Question related to that. So I think those rivers bring a lot of soil also with them.
Yes.
So what happens to that soil near the dam? Does it get blasted somehow, or does it get stuck there and eventually fill up the reservoir?
Basically, yeah, it fills up the reservoir in the end, if the soil is coming from upstream. But I think in the Nile, the thing is that the soil is getting eroded downstream from the dam. So it's not actually coming from upstream of the dam. So it's not that kind of a problem. They don't need to actually pass the bits of soil through the dam. They just need to get the influx of water to get the soil into the stream and then to the farmlands downstreams. But yes, basically, if you have a dam, it'll form a lake, and a lake is going to fill up in the end. As we know, in Finland, we have quite a lot of swamps that sometime in the past were lakes. That's something that happens. Lakes fill up and become swamps, and then at some point someone drains the swamp, and then there's arable land or something. And also something to mention, the size of the reservoirs vary by the size of the dam, actually, and by the time. For example, at the Three Gorges, depending on the what time of year you measure, the reservoir is going to be hugely different in size, both in the area of the reservoir surface, as well as the amount of water, or the volume of water in the reservoir. And for example, the Three Gorges Dam reservoir is up to 40 cubic kilometers of water when it's at high tide or high capacity. That's quite a lot of water. Maximum safe output power, about 25 gigawatts. Three Gorges is at 22.5 gigawatts. Most catastrophic failure mode, structural disintegration. So basically, the dam breaks. And now we have a dam that holds back 40 cubic kilometers of water, which is quite a lot of water. And suddenly, the dam is not there anymore, and the water is free to flow where it wants. We get quite a lot of fatalities suddenly. So here we start getting severe fatalities. The site is going to be, you know, it's going to need rebuilding of some sort. Probably, if you have any of the dam left, it's not going to be structurally sound enough to actually be used as a dam anymore. So first you need to start by tearing down the rest of the dam that wasn't broken. And then you can start planning about rebuilding the dam. And the fatalities are going to be, well, a lot. Depends on whether you have a city that is situated right under the dam or not, and so on. Then moving on, modern windmill. This is actually quite easy. Provides electrical power, requires the modern era. Miniaturizing, I can't even speak. Anyway, creating an electric generator that is small enough and reliable enough to actually put inside a windmill housing and build, you know, tall enough windmills to actually generate any kind of, you know, efficient amount of electric power needs quite a lot of things from your structural engineering. Turns wind to electricity via mechanical rotation. Possible additional hazards. Are citizens concerned about infrasound, if you happen to have those? And bats, yes, yes. Yeah, exploding bats, yes, it's terrible. Safe output power, 1 to 6 megawatts per windmill, depending on, of course, how much wind you have, how you actually build the windmill. Catastrophic failure mode is mechanical failure, again. Not going to cause a lot of fatalities. The worst that I can imagine is actually one of the blades of the windmill breaking off the windmill while it's you know, turning. And well, you have, what, 20-meter long steel, tapered steel particle that is flying at some speed in a random direction. When it's going to come down, it is going, let's just say, it is going to have quite high value in armor piercing in your system, any system that you use. But then again, it's only a single spear, so you'll kill a few people. Or, well, you could kill more than one people, but they need to be standing in a really, really long line. But yeah, this is easy. Then we have electric engine from battery power.
About windmills, there's actually so much power and motion that the thing actually can catch fire pretty easily if there's too much wind.
Oh, yeah.
Might be the blades on fire also.
Oh, yeah, true. So add what? D8 fire damage. In addition to the, what? 20 something dice of, you know, piercing damage. But yeah, electric engine from battery power. So this is your electric cars. Generates mechanical power from by converting previously stored electrical energy with a motor. So this is, I added this because this basically, it's a self-contained thing that generates mechanical power. So electric motors other than this are not on the list. And yeah, quite a lot of things here depend on how the electricity is actually stored. Yeah, with sufficiently ingenious methods of storage, the impact of this method can be increased quite dramatically. If you store your electricity in open vats of acid that you for some reason lug around on your train, then, well, just by, you know, tilting those barrels, you are going to have probably more impact than what is considered here. Up to about 280 horses. This is again in horses because these are meant for vehicles. So they are not, we are moving, for a while we are moving down from the power plant size. Most catastrophic failure mode, battery containment failure and or runaway thermal event. So basically either the batteries that you have, which at least in some cases are filled with acid, the containment breaks and you have a pool of acid that is moving in a direction fast. It is not good. Or the battery packs actually start heating themselves up in a ever-increasing rate until they set themselves on fire and the vehicle around them on fire, at which point you are going to have burning metal and burning acid moving at a fast pace in one direction. So, yeah, acid and fire damage. That's going to kill a lot of trolls. Impact, well, this varies because it depends on the size and construction of the batteries. So if you have a small motor and a small battery, you're not going to kill anybody. But if you're actually powering a truck or a train, you are going to have huge batteries. So it depends. Moving on, this is the modern power plant. So steam turbines, basically, you can power them by burning different kinds of things. Coal, oil, and gas are the ones preferred in this timeline. If you have something else that burns really well, like mummies, you could use those as well. But I haven't heard of any country building a mummy power plant. If someone does, please do tell me. Generates power by running steam turbines with pressurized water vapor created through burning various fuel sources. Basically, steam turbine, the steam engine can create rotational power, and you can add electric generator, the proper electric generator, into that axle, and it creates electricity. That is how the first electricity generators worked. But a steam turbine is basically the same kind of thing that you have on jet airlines. The jet airline engines, for example, are turbine engines. So it's a highly efficient method of transforming pressure of, say, steam into rotational energy. So this is basically, engineers managed to create a highly efficient method of turning pressure into electricity. So that's basically why most things use steam turbines nowadays, if they want to, if they are really, you know, serious about generating power. Maximum safe output power is 5.6 gigawatts. There are actually 5.6 gigawatt power plants of coal, oil, and gas separately built around the world. Apparently, currently, the largest power plant that we want to build that burns something is 5.6 gigawatts. Of course, this can be increased if you increase the strength of the materials used in the turbines, but basically, in a modern setting, that is about this is approximately the scale where we are. Most catastrophic failure mode is pressure rupture. So, as I mentioned, these use pressurized steam. So, one part of the system is going to break because it just can't withstand the pressure anymore, and then it breaks. Then the pressure is released. Now, one thing that affects the impact of here, which is actually, this is the same level as a steam engine, but this is actually on the low side of that, because unlike steam engines, steam turbines do not require a constant, they don't require a pressure vessel. So there isn't going to be a huge tank that has been pressurized. There's going to be lots of pipes that have been pressurized. But the total volume of pressurized steam is going to be lower, so if a rupture happens, it is not going to be as catastrophic as for a steam engine. So basically, there is danger to the plant employees if they happen to stand right next to the pipe that bursts, or if they, you know, for some reason hit one of those pipes with a hammer and actually cause it to break, then, well, yeah, they are going to have a bad time. But other than that, yeah, not really that much. Anyone outside of the power plant is not going to be affected, other than, of course, what happens when you lose electricity suddenly. So that's going to be a problem. But other than that, they're going to be fine. And in the worst case, it is possible that the pipe breaks in such a place that they actually need to, you know, tear down walls to actually repair it. So, yeah, the power company is not going to like this, but it's not, it isn't anything. At worst, it can bring down the power plant for a few months, but other than that, this is not that much of a not that big of a deal. Then, moving on, next step, the nuclear reactor, or the fission reactor. It's just that since we don't have, currently, we don't have any other nuclear reactor types, we just use nuclear reactor to mean fission reactor. But, you know, if you move to a sci-fi setting, you can't talk about nuclear reactors. You need to talk about fission reactors, just so you know. So now we need the atomic era. We need to know quite a lot about things on the atomic level. And again, this generates electrical power. And also, for your information, this is why I started holding this lecture. Because generates power by running steam turbines, the same as we had previously, with pressurized water vapor created through controlled fission reaction. And here we go. There is a difference between nuclear reactors and meant for electricity generation and a nuclear bomb. They require totally different engineering. The intention behind them is different. They use different fuel, actually. Nuclear reactors require fuel that has, what, about 2% of fissile material in them. Nuclear bombs require fuel that has purity of at least 99%. So there's a world of difference between the stuff that you put in them, let alone the actual engineering behind them. Maximum safe output power. There's a Kashiwazaki Kariwa plant in Japan that has a power output of 8 gigawatts, or had, before they shut it down due to, well, the recent craze. Most catastrophic failure mode, core meltdown or pressure rupture. Pressure rupture is actually the same one that we had for steam turbines, because, well, these use steam turbines. Impacts, we get on the next step on the scale, but still, this is not, to be honest, nuclear accidents are not the fearful thing that some people think they are. They are bad. I'm not saying they aren't, and they can cause severe fatalities, especially if they are not contained properly. But it is not the same as somebody exploding a nuclear bomb. And if you have a movie where they have a nuclear reactor and someone goes in there and throws a few switches or removes a safety feature, the nuclear reactor is not going to cause a mushroom cloud. Oh no.
Also, it was not just about every single movie nuclear reactor. Some place at some point called it's going critical, which is what a nuclear reactor should do.
Yes.
Going critical, it means it's generating energy.
Yeah, nuclear reactor needs to be critical to actually generate energy. If it's not critical, it doesn't generate energy. But yeah, so basically, if a nuclear plant or nuclear accident is contained properly, if the plant practices are, handled properly, then nobody outside the plant is going to be affected. And the worst that this can actually affect people outside the plant is by the release of radioactive material from the plant. And that basically means that the plant has generated too much pressure inside, and they need to release some of the pressure to keep the plant from actually exploding. But the explosion is going to be caused by the pressure, the steam generated inside the reactor housing. Not the nuclear reactor, the nuclear reaction is not going to be exploding. There isn't going to be a nuclear explosion in a nuclear plant.
Both of those, both the core meltdown and the pressure rupture happened in Chernobyl.
Yeah, they did. But the problem with Chernobyl is that there was a core meltdown, and the plant didn't actually have the modern safety features that contain a core meltdown, which is basically the nuclear core melting and flowing into a pool of slag at the end. Yes?
And in Chernobyl, they used burnable to slow the fission.
Yeah. They used coal to slow down the fission, which is like, no, don't do that. And the problem was that what happened is that they didn't do what the Japanese did when they had the latest nuclear problem. In Chernobyl, they did not, release slowly the pressure that was being built up in the reactor housing. So they let it build up until the whole reactor building just gave up and blew out in one big go, releasing a lot of radioactive material into the atmosphere. If they had, say, opened a window and just let some of it, they would have still released radioactive material into the countryside, but it would have been contained, or not contained, but limited. So it wouldn't be like people talking in neighboring countries that where is the cloud going to go, but it's just, it would have been a lot different.
Sorry, is that steam radioactive then?
Yeah, basically. There's going to be radioactive particles, isotopes that have been mixed into the steam. The steam itself is not going to be radioactive because it's water. So water doesn't really turn radioactive that much. But anyway, so this is why I did this. And actually, I am running out of time fast. God damn it. I'm really sorry. Because now we start moving into the sci-fi section, which I thought I would be spending most of my time in. So, I'm really sorry. I need to go through these quite fast if I want to get anywhere near the fun part. Fusion reactor. Future tech. It is always 30 years from now. Always. Generates power by running steam turbines. The same things that we have. Only thing that has changed from previous ones is that we heat the steam by a controlled fusion reactor instead of a controlled fission reaction. And the specific method that we use for plasma containment, so fusion reactors usually require a contained bottle of plasma that is quite hot to actually work. And the specific method that we use for plasma containment, and ignition, the creation of the plasma, and how we start the reaction, they just mostly affect the likelihood of a catastrophe. They don't really affect what happens if there's an accident. Maximum safe output power, gigawatt to terawatt range, easily. Depends on your steam turbines mostly. Most catastrophic failure mode, plasma containment failure. Now we get to the fun parts. Anything that has containment failure is, in my opinion, quite fun. But anyway, what happens? Well, we actually get a bit further away from the fission. because now we have a varying amount of plasma that is released at high speeds in any direction, possibly every direction. And the plasma is probably going to be several million degrees Celsius. So it's not only going to cause burns, it's going to actually, vaporize people. It is also going to melt anything that you put in between them. And plasma is usually contained by magnetic fields. That's what you do because you can't really touch it. Nothing. We currently don't have stuff that can stay stable at those temperatures. That's the point of plasma, actually. So yeah, there's not really going to be, once the initial containment has failed, there isn't really anything that we can do. The plasma is going to go wherever it's going, and it's going to destroy things until it cools down enough.
Reaction should be that catastrophic because the plasma is very diffuse. So the moment the magnetic field goes down, the plasma touches the walls of the reactor, slags the reactor, and then immediately cools down because there's not really that much of plasma in there.
Yeah, but as I said, this depends on the amount of plasma that you have. Most modern reactors are built with small enough amounts of plasma that, it's mostly just going to slag the reactor. But if you have miniature, I just can't say the word. Anyway, smaller fusion reactors, for example, in a vehicle or something, they might have a relatively larger amount of plasma, which might cause problems. So, but yeah, most likely it's not going to be. This is the worst that can happen, as I said. Then we have the orbital microwave emitter, which is basically, again, future tech. People have been talking about building one of these. So we generate power somewhere up there, and then we simply move the energy down here by building or by beaming it down as a focused beam of microwave energy to a receptor facility on the ground. And no, this is not a laser cannon, nor a death beam. That is simply absurd to try to say that this is. Maximum safe output power, again, terawatt range at least, petawatt range possibly. Most catastrophic failure mode, accidental beam misalignment, if you want to get politically correct about it. And we get severe fatalities. You have a highly powered microwave beam that is moving somewhere where it shouldn't be. It is going to basically, if you know what happens when someone turns a, future tech mining laser that is meant to mine asteroids and starts pointing it at, things, it's going to cause damage. There's going to be this line that is going to be molten. And if there were buildings there, they are not going to be there anymore. There's going to be, the saying, like a hot knife through butter comes to mind, to be honest. Yeah. So basically, the amount of fatalities depend on whether you do this on a major city or in the countryside. Yes?
There is a microwave emitter accident in the intro of a game called Vanquish, which basically obliterates San Francisco in a matter of seconds.
Yeah, easily done.
Someone made a funny suggestion that it might be more cost effective instead of beaming down the energy from orbit to just mine Bitcoin on orbit and then beam Bitcoin.
Yeah, well, this is not a lecture about Bitcoin. I have opinions, let's just say. But yeah, moving on. We have a thermal borehole, so MOHO mine. Geological engineering. They are trying to drill down in Russia. The deepest point in Earth or deepest artificial point on Earth is in Russia, and they aren't nowhere near the depth that we would need to actually have a thermal borehole properly. So we have an open hole into the Mohorovičić discontinuity of the planet that this is built on. So basically, we go through the whole crust of the planet to the molten mantle, and we have, a straight hole to the mantle. And then we pipe water down, it gets turned into steam, we pipe the steam up, and we run steam turbines. Easy, cheap also. Yeah, so what is the worst that could happen if you actually open a, open hole to the mantle of the planet? It's like, come on. Maximum power, safe output power, we are easily in the petawatt range. Catastrophic failure mode. We need to have some kind of shielding to actually keep the hole open and the mantle from bursting up. So basically that shielding collapses for some reason. Someone forgets to, or someone turns off the shield, flips the switch, or just, pulls a plug to get the vacuum cleaner in the same place. And yeah, now we start getting damage, because depending on how large the borehole is, what's the diameter, where it is, and of course what the size of the planet is, it is anyway going to create a supervolcano, a violent supervolcano that just suddenly turns on, but it might be even worse than that. So this is going to cause extinction of species. Possibly not humanity or whoever did this, but that's in the cards. Moving on, we have biological heat harvesting, which requires usually the robot revolution to have happened. And we generate power by harvesting the excess body heat of biological or captive specimens. Do note that it is usually much more efficient to just devote any resources you are trying to put here into other power generation methods and just exterminate the species that you are trying to use for this type. It is much better, just as a tip. Safe output power, petawatt range, again, depends on the size of the facilities. Most catastrophic failure mode, containment failure, or / rebellion. And yeah, well, depends on the size of the containment failure of the biologicals, and of course, whether the actual human revolution succeeds or not. But yeah, it's possible. Do use something else. It's much safer. Then we have cold fusion reactors. This is usually much further than fusion reactors because, well, this needs something weird to happen, at least according to current scientific understanding. And generates power, again, by steam turbines, but now the fusion reactor is actually handled in room temperature conditions. We usually get terawatt range, depends on the size of the reactor, but terawatt range is possible. That is the maximum. You can build smaller if you want. Basically, most catastrophic is sudden output failure. Nothing really. As I mentioned, it's going to be in room temperature, so it's just going to stop generating power. I don't really see how this could basically go wrong. So if you want to play it safe, use this. Because then we move to the fun stuff. Antimatter reactor. Now we generate the heat, or the thermal energy, with a matter-antimatter annihilation reaction. We are, again, in the petawatt range. And the failure mode is antimatter containment failure. That's always fun. So yeah, the impact depends on how large of a how much of the antimatter you've stored for use in the reactor. If you used, a large enough containment, you can actually blow up planets easily. But other than that, you are probably going to scrap the reactor at least. And your vehicle or vessel is probably going to be, well, rapidly expanding cloud of dust. Then we have gravitationally assisted generator. So this needs artificial gravity, some sort. And this is basically any of the earlier ones, but you just use shaped gravitational fields to assist the steam turbines in running at increased power output levels. Petawatt range, easily. And, well, gravitational anomaly release. If you have artificial gravity, it depends on what that means. But impact, again, this can destabilize planets easily if you have large enough reactors. This is, as a side note, this is actually what the drive core in Mass Effect is. It is basically, they use the element 0 in the universe to create artificial gravity fields inside a normal, I think, fusion reactor to actually assist the process. So, just so you know, that's why this is here. Then there's the stellar rotation generator. Now we start needing stellar engineering. And we have two stellar mass bodies, usually extremely small pieces of neutron stars or neutron star material that have been caused to rotate around a common center of gravity, and they create quite a lot of electromagnetic radiation and gravitational waves, and we harvest those to generate the power. This is fun. Now we start getting to the Kardashev scale, so 1 to 2, depending on the size. Usually anyone that can actually, that can't harvest the energy of the local star probably is not able to create one of these devices. But you can build smaller versions that don't provide that much energy. So yeah, violent pair destabilization event is the failure mode here, which basically means that for some reason the pair of the stellar mass objects do not no longer, or don't any longer, rotate around each other, but start going their own different ways. They basically split up like certain rock bands. So yeah, this is if you happen to be near a planet, you most likely have about 50-50 chance of one of the stellar mass objects flying into said planet. And when you have a planet and an object that has the mass of a planet combining violently, it's going to cause problems for the structural integrity of said planet. So yeah, as I said, depends on where you are. If you are in interstellar space, so there aren't any stars or planets around, you're just going to wreck your own vessel, but other than that, it's fine. Then there's the Schwarzschild Google Blitz reactor. Lovely name, lovely name. Generates thermal power, needs singular containment, and generates power by harvesting Hawking radiation released by a captured artificial singularity. At this point, I really don't have the time to go through this theory, but this is theoretically possible. 1 to 2 on the Kardashev scale, singularity containment failure again. So basically, we have a rogue singularity that is going somewhere in some direction, probably fast. Not a good thing to release a black hole in your local stellar cluster. Stellar siphon. So we basically just draw stellar gas from the local star and use that for energy creation. Again, 1 to 2 on the Kardashev scale. And yeah, once you start messing around with your local star, pray to God, or whatever you use, to not cause a supernova. Because this can actually sterilize parts of the local galaxy cluster. At least the nearby systems are going to be scrapped in a few years. Dyson sphere swarm encapsulate a whole star in an artificial construction. 2 on the Kardashev scale, by definition, actually. Stellar containment failure, so you have the star going in, or the Dyson sphere colliding with the star. This is actually just going to wreck your Dyson sphere. So, but then again, anyone who builds this usually has civilization built on the Dyson sphere. So by definition, that civilization is going to be in trouble. Yeah. Then there's super-variant scattering generator. This is actually fun. This is basically a Dyson sphere around. Okay. Apparently I've run out of time, and I just got to the fun stuff. I am terribly sorry for this. If you want, I can show you these slides outside this lecture hall right after this lecture and go through these privately or in a smaller group. Thank you very much, and sorry for this.